see how can I do this. Actually, I was sharing the full screen. Let me just try again. But it's fine. It's not a problem. Okay. So should we start, or are we waiting for more people?
No, please start. Please start. Yeah.
Okay. So yeah. So hello everyone, and yeah, thanks for attending this talk. Where I'm actually excited to talk about my PhD work, the work that I've done at ETH Zurich, where I was a PhD student until August. Since then, I moved to MIT as a postdoctoral fellow, as Nick was already said. So this is work done together with my great collaborators, Gary, who's also a PhD at ETH Zurich, Professor Thomas Hoffman, who is our supervisor, and a bunch of students that we supervised for master theses and bachelor theses during the last 2 years. So I'm going to talk about non-Euclidean representation learning, and I'm going to focus mostly on spaces of constant curvature. I'm gonna detail later. And yeah, so I'm gonna focus on discrete data such as words, entities, and especially hierarchical structures. Okay, so as you all know, we want to do machine learning on discrete data. So the way to do it is, for example, knowledge graphs, like the one you see here in the picture. And the typical way to do it is to embed this discrete data. So if we have words, we want to embed each word and then have a compositional layer on top of this and word embeddings in order to embed large pieces of text like sentences or paragraphs. If we have knowledge bases, we want to embed maybe each node or each edge in the knowledge graph or both, and maybe again have some compositional layer on top of it that is able to capture interactions. So yeah, so that's the general pipeline. And what do we do with these embeddings? So we can use them in downstream tasks. For example, we want to do machine translation, or maybe we want to do sentiment analysis for text. We want to understand if a review for a movie or for a product is positive or negative. Or we just want to do clustering. We want to discover in an unsupervised fashion topics in the data or particularities in subgroups of our data. And last but not least, maybe we want to do something on graphs, so on more complicated discrete structures, where we want to do classification or even graph generation nowadays for, let's say, molecular data. Okay, so the typical like workhorse for embeddings is to use Euclidean geometry. So the goal here, so in general, we want to embed data in a geometric space, right? And Euclidean space is like the simplest one. And we kind of have like 3 goals in mind when we do that, maybe implicitly or explicitly. So what we want to do is we want to capture semantics via distances, via geometric distances, so distances in these spaces. So maybe we want semantic similar entities to be close in this space. For example, cities like New York, Beijing, Paris. And maybe semantic dissimilar entities should be far away. So maybe New York and airplane are not so close in semantics. So maybe we want them to be far in the space. And last but not least, maybe we want geodesics, or like what we know as being straight lines in Euclidean space. We want them to be semantically meaningful. So one example is like doing a word analogy, as you all know, like this king, queen, man, woman example that's very popular. So a fundamental question that I'm trying to take steps towards in this talk is, what is a good embedding geometry to capture the global similarity structure of the data, and maybe not also just similarity, but more complicated structure like hierarchical structure. So what do I mean by good embedding geometry? Well, it has to be a geometry that gives a good inductive bias or a good prior for some assumptions about the data that we are using. So I'm going to have a few slides now where I'm going to have an overview of challenges and contributions that I'm going to cover in this talk. So one interesting aspect is how to learn good embeddings such that we capture the underlying hierarchical or entailment structure. Okay. And I'm gonna focus on, in particular, on the hyperbolic space because that's the focus of my PhD and of this talk. So in this example here that you see this picture, let's say we have the WordNet tree, and one example is we have the node that represents animal, like the generic concept of animal, and then we have sub-concepts which are mammal, or maybe some animal with wings, some class of animals that have wings, like birds, and then we have a subclass of all of these two, which is, let's say, the bat. So we want to be able to embed this type of data in a meaningful way. So what is a hyperbolic space? So hyperbolic space is a non-Euclidean space which acts as a geometric prior for hierarchical or tree structures, or just data that has a heavy tail distribution, like scale-free or scale-free networks that follow power law distribution. I'm gonna show more in a second. So here on the left side, you can see the hyperbolic space is essentially constrained to be in a ball of fixed radius. So embeddings are embedded in such a ball. And these black lines, these black curves that you see here are actually straight lines in this space. So they are essentially the curves that connect the 2 points in the shortest, using the shortest distance. So if you want an analogy, you know that if you travel, let's say from, I don't know, from San Francisco, let's say to, I don't know, Berlin, then you usually don't follow the straight line on a map, but you follow what is the shortest path on the sphere, on the Earth sphere. So this is like a good analogy to understand what these shortest paths are, these geodesics. Okay, so I'm gonna cover a paper that we have submitted at ICML, and that has been published at ICML 2018 regarding this aspect. So it's gonna be one of today's focus. And the second aspect that I'm gonna talk about is how to simultaneously capture similarity and hierarchy in the embedding space. So for example, how we can do hyperbolic word embeddings. And let's say we don't want just to have word embeddings that are good to capturing word similarity or word analogy, but maybe you also want word hypernymy. So we want to know if something is a sub-concept of something else, just based on looking at the embeddings, the corresponding embeddings. And here we have a publication, if you're interested to read all the details, that's published at iClear 2019, actually. Sorry, so there is a small mistake here. And the last aspect that I'm going to talk today about is how to use these non-Euclidean embeddings to perform downstream tasks. So how to design and use hyperbolic neural networks that are, or hyperbolic deep learning tools that are able to respect this geometry. And here we have this hyperbolic neural networks paper that was presented at NeurIPS 2018, and it also had a spotlight. So you can also refer to the paper for the full details. Okay, so now a few introduction slides about hyperbolic geometry and how we can use it in machine learning, or how people have started to use this hyperbolic geometry in machine learning. So as you know, almost all machine learning or deep learning pipelines, they assume Euclidean geometry. And why is this? Like, the reason is simple. It's the simplest geometry. It matches very well our 3D intuition. It's well studied. It's a powerful formalism. It has very simple and efficient formulas, let's say inner product, L2 distance, vector addition, scalar multiplication, linear interpolation, and so on. And they're very computationally, these are very efficient, and they work very well. However, there are some constraints of Euclidean geometry that might hurt one depending on what type of data is used. So people typically capture similarity of like discrete objects using dot products. Can everybody hear me still, or is it?
We are still here. We can hear you.
Great. I'm gonna continue. Okay. So, so we typically capture similarities using dot products, and these dot products are functions that are constrained to be positive semi-definite if we work in the Euclidean space, which means that if we build the so-called Gram matrices, which are just matrices where if you have n objects, you just build the matrix of pairwise similarities, then these are constrained to be positive semi-definite. And as I'm going to talk a bit about later, this is a constraint. So we cannot embed large classes of graphs without low distortion or loss of information. For example, cycles or trees. So you see here like very simple graphs which represent a cycle on the left, and on the right a very simple tree. And using this type of Poincaré type inequalities, one can actually prove that these graphs cannot be embedded in Euclidean spaces of any dimension with distortion less than square root of 2 and respectively 2 over square root of 3. So here one would be perfect, would be a perfect distortion, which would mean that the graph distances are exactly matched in the embedding space. And bigger than 1 means already we encounter some distortion. So we cannot really place, let's say, this square on the left. We cannot place it in any Euclidean space such that the graph distances are exactly matching the embedding distances.
So the distortion is. Oh, sorry, Nick. Go ahead.
Yeah, go ahead. I'll ask this.
So the distortion is how much like you have to pretty much distort the distances such as to map it to the Euclidean space.
Yes, exactly. So I didn't put the actual formal definition of distortion here. It's actually the standard one that's used when people talk about graph embedding distortion. But intuitively, what it is essentially you measure the embedding distance between two nodes, between the embedding of the two nodes, and you want that to be as close as possible to the graph distance, which is the length of the shortest path in the graph. So in this case, it's going to be 2. The graph distance is going to be 2 for the two opposite nodes in the square. Whereas if, like in this picture that's shown here, is actually square root of 2 in the Euclidean space. So in practice, it turns out you cannot put this square in any Euclidean space with a distortion less than square root of 2. So if you want, it's like the ratio of the embedding distance over the graph distance. It's something like that. So it's not exactly that, but it's like something like that, like the average ratio.
Yeah, it makes sense. The concept makes perfect sense.
So what you're trying to embed over here is 4 nodes that they all have a distance of 1 between them. It's like a click. And
no, not exactly. The distance between two opposite nodes is going to be 2 because it's the graph distance. So, the graph is just a cycle of length 4.
Okay, so you can match the first one. So I see what you're saying. So the distance between neighboring nodes is 1, but the distance between two hops has to be 2. But here is square root of 2, and the same thing with the star.
Yeah, it's square root of 2 in this particular embedding, but you could maybe come up with different embeddings. You can stretch it in different directions, but it's not gonna get you a better distortion than this specific embedding here.
I get it. So the graph distances, which is hop distances, cannot be preserved.
Yeah,
the shortest path.
Yes, one very simple way to see that it cannot be preserved is that it's not gonna satisfy triangle inequality, in the sense that the distance from the two opposite nodes is actually the sum of the two distances in the triangle. I cannot really show here, but anyway, so triangle inequality is not satisfied in any. So in any metric space, you cannot get a perfect distortion. But what it turns out is that you can actually put any cycle in a spherical space with arbitrary low distortion, so 1 plus epsilon for any epsilon that's arbitrarily low. And the tree, you can put it in a hyperbolic space with arbitrary low distortion. So again, 1 plus epsilon, where 1 is perfect.
Okay, that was clear. Thank you.
Okay, yeah, feel free to interrupt if you have any other questions. Okay, so the Euclidean spaces can model perfectly only intrinsically flat manifolds. So these are manifolds like surfaces, if you want, that can be stretched without encountering any distortion, and they can be flattened. So they can be put in like a completely flat, let's say, sheet of paper. So just to give you another intuition of this is sometimes, let's say, we have to deal with data that's known to not lie in an Euclidean manifold. One example is, let's say, spherical data. We cannot take a sphere and completely flatten it without large distortion on a flat sheet of paper. And the typical example is how to represent maps of the world on a flat sheet of paper. And people typically use what is called the so-called Mercator projection. That's the typical representation of maps. But it's kind of misleading if you see here on the left side, like in this projection, Mexico and Greenland appear to be very, very different, but it turns out they actually have a very, very similar surface. So you can actually see where's the distortion happening. And on the right side, I'm showing here the United States map. But if you just translate United States, like to be close, let's say, over Finland, then the representation under this projection is going to show a much larger surface, right? The same for Australia, if you want. So there is lots of distortion, and these maps can be a bit misleading, right?
So that's amazing. I never thought that. I always thought that Greenland was huge, but I never thought it's as small as Mexico.
No. Yes. Okay, and it turns out that this short diagonals inequality that I'm showing in this slide is actually very useful to prove all sorts of distortions in the Euclidean space, including the distortions for cycles and trees that I was talking about earlier. I have actually more details about this in my PhD thesis. I can send it to you if any of you is interested. So it turns out to have a fundamental limit, so we can only learn what we can represent. So I'm gonna motivate a bit more why Euclidean spaces are too narrow for tree-like or hierarchical structures, tree-like graphs or hierarchical structures. So let's say we have a tree and we want to embed it in the Euclidean space, and the idea is that we want to embed it such that nodes that are connected by an edge, they are close in the embedding space. If they are not connected by an edge, then they are far in the embedding space. And ideally, we also want to capture the distance in the tree. So we want to capture the shortest path length between two nodes in the tree, also in this embedding space. So if we have a single node, that's very simple. We're just going to put it in anywhere. Now, if we have a tree with two nodes, with two leaves and the root, it's very easy again. But once we start putting more and more nodes, well, so far so good. We have a very small tree here, and as I said before, vertices are close in the embedding space if and only if they are connected by an edge. So let's say the tree grows. Let's say we are dealing with more realistic, like big hierarchical structures, and you can actually see here that the outermost leaves are becoming increasingly close to one another. And even though they are not connected by an edge in the graph, they start to be very, very close. If you look at leaves corresponding to different branches of the tree, you will see that they are becoming closer and closer, which is not exactly what we wanted from a good embedding space. So yeah, so things get worse here, and we have lost our nice property, which was closing the embedding space if and only if they share an edge. Of course, you can argue here that we can just increase the dimension of the space. This is true, but asymptotically, we still have a problem. I'm going to discuss about it a bit later. So yeah, so if the trees are getting larger and larger, then we have a problem. So yeah, so what is the problem? The problem is that the Euclidean the volume of an Euclidean ball, it only grows polynomially with a radius. So if we're in dimension D and we have a radius R, then the volume is proportional to R to the power of D. And this is a problem which is why we quickly run out of space when we are dealing with structures which have an exponential volume growth, like trees. So in the trees, the number of nodes on each level of the tree grows exponentially with the tree level. However, if we use the so-called hyperbolic space that I'm going to detail now, in this space, the volume of a ball grows exponentially with the radius. So it's the formula shown here. So why is this bad? So if you see here, we have these two nodes that are two leaves, and the Euclidean distance of their embeddings is very, very small, but the tree distance is very, very big. So you have to go to the root and back in order to get the tree distance. So you can see here that the embedding space already lost its nice property of capturing the graph distance. And here is another like kind of maybe in picture to give some intuition. Here on the left side, we have the hyperbolic ball, and each bed in this figure has the same hyperbolic area. But of course, if we would view this picture in the Euclidean space, then they would have different areas, right? But in the hyperbolic space, they have exactly the same area. So you can see that the space behaves very similar to Euclidean space if we look, let's say, in the center of the ball. But once we go far away from it, the geometry is kind of behaving a bit funny. So it's more like it kind of has an exponential volume growth, which allows exponential space growth. Okay, and the first paper that tried to use these hyperbolic spaces in machine learning was published at NIPS 2017, NeurIPS later. So what they want to do is to measure similarity not in Euclidean, but in hyperbolic space. The reason being, like what I already discussed, is a continuous analog of trees. It's a good prior for hierarchical structures and scale-free networks. So what are scale-free networks? They are graphs for which the degree distribution is basically heavy-tailed. So here I'm showing the log degree distribution of these graphs. And you can see that the random networks, the network behaves a bit like a Gaussian distribution of the degrees, where a scale-free network or a hierarchical network, they have like a more similar degree distribution. So hyperbolic spaces are very good for this type of graphs. And of course, they are very well studied. These spaces are very well studied in mathematics since like a long time ago and in computer networks. So what is a hyperbolic space? It's a metric space where the distance function is given by the formula here in like shown here. And you can actually see, again, I'm showing this picture where all edges here, they have exactly the same length under this distance function. And geodesics, or straight lines or shortest paths between 2 points, are shown in this animation here. So you can actually see that we have a congestion at the center, a higher congestion at the center than at the border of the ball. And that's because geodesics tend to bend inwards. And that's maybe why you can actually see a good inductive bias for this being good for embedding scale-free networks. Because in scale-free networks, like a few nodes form a core of the graph with high connectivity to the rest of the graph. The same, like, let's say, for trees. So hyperbolic spaces are Riemannian manifolds, and I'm not going to cover aspects of Riemannian geometry because this is like it's going to be a very long discussion. But I invite you to read about them if you don't know about these concepts. But what I'm gonna say is that this hyperbolic space is a Riemannian manifold with a particularity. It has a constant negative sectional or Gaussian curvature that I'm gonna talk a bit about later. So we are interested to work with common concepts from Riemannian geometry, which is the tangent space, geodesics, exponential map, Riemannian metric. So these are all concepts that we need for using this in machine learning, this space in machine learning. So yeah, so just to give you a little bit information about or intuition about curvature. So we have three big notions of curvature. One is sectional curvature, the other is Gaussian curvature, and the last one is like Ricci curvature. For hyperbolic spaces, they are all the same. Like these spaces are spaces of constant curvature, negative curvature. So in general, let's say if you have a surface, then sectional curvature is a curvature at a point with respect to a direction. So if you see here, we have this red point and we have the green direction. And then we can measure how curved the surface is if it's like sectioned along this, let's say, this curve. And if this curve is bent, let's say, inward, then we say it has a positive curvature. If it's a straight Euclidean line, then we say it has zero curvature, and if it's bended outwards, we say it has a negative curvature. So that's a bit of intuition of what a sectional curvature is, and now a Gaussian curvature. So if you have a surface, 2D surface in 3D, then in order to compute the Gaussian curvature, you just have to find the two sectional curvatures that are the largest and the lowest. So in the case of a cylinder, it's going to be a positive value, which is a green sectional curvature, and the zero value, which is the smallest curvature. And the Gaussian curvature is just the product of these two numbers. And it like a bit counterintuitive is that the cylinder is going to have a zero curvature. But if you want to understand a bit why is this true, then you can actually take the cylinder and you can cut it in one, like you can just do a single section, and then it's going to be completely flattened on a flat sheet of paper. And you cannot actually do this with a sphere, let's say.
So the Gaussian curvature on the cylinder is going to be zero, but that's only for the cylinder, correct?
Exactly. It's only for this particular.
Okay, yeah, I got you. Yeah. Thank you.
But so let's see. Actually, I have more examples. So here we can see three examples of constant negative Gaussian curvatures. Constant means that at every red point is the same value, right? So on the left side, you can see a negative curvature where the surface is behaving locally at every red point, at every point, like a saddle, right? So you have two sections, the two opposite extremal directions curve in opposite directions. And then you have the cylinder or a flat sheet of paper where they have zero curvature, and on the right side you can see the sphere where the curvature is where the sectional curvature is constant and positive at every point in every section. And so the hyperbolic space is a space of negative curvature, so it's going to correspond to the left picture. So triangles, they behave differently in these spaces. In the Euclidean space or spaces of zero curvature, the angles of the triangle sum up to pi, as you know. If we have a negative curvature less than pi, and if it's a positive curvature is more than pi. So here I'm showing a street picture, sorry, of geodesics in the street spaces. So K, I'm going to use K to denote the curvature from now on. So -1 is the hyperbolic space, and zero space is the Euclidean space. And then on the right side, I'm showing the stereographic projection of the sphere on a plane. And that's how the geodesics on a sphere, they look like when projected on this space. So if you want to see more, you can visit our blog. Here I'm also showing the distance heat map for different types of curvatures. So again, positive curvature is sphere, zero curvature is Euclidean space, and negative curvature is hyperbolic space. So for negative curvature, we have to constrain the space to stay inside the ball of a fixed radius. Okay, I'm gonna cover a bit the so-called concept of parallel transport. So parallel transport means we are, let's say, at a point X, and we have a blue vector that goes in any direction, and we want to translate it to a point Y. So there is an entire mathematical formalism of how you can do that on a Riemannian manifold. So it's not as trivial as in an Euclidean space, or not as straightforward. And here I'm just showing a picture of how it actually looks like. So the two blue vectors, they show how the vector from X is parallel transported to Y.
So this is fascinating. Shows how the coordinate system is changing by going from X to Y. So computations that you will do if you were at X, that's why we see all these vectors bending. This is how they look from the X perspective versus Y perspective.
Yes.
Isn't that right?
Yes. That's true.
But within Euclidean, it's really simple. You just change the origin of the coordinate system, and that's it. And
Yes.
Some things that, when you're at X are very close. If you go to Y, they can be further away. Very fascinating. Good animation.
Yeah. We actually used exactly this concept for word embeddings. When we trade word embeddings in this Poincaré glove paper, we actually use this to adapt the analogy translation that's used in word2vec.
So I think that's really great when you mentioned that the space is a prior, which means that not every point is equivalent in this. Like in Euclidean space, it doesn't matter where you are, all the points are the same. They don't really have any information. But here, depending on where you are, things change. Would you say that's right?
Yes and no. Yes and no. Actually, in these spaces, you also have a concept of, so the origin doesn't carry, the origin of the space doesn't carry any particular meaning. You can still translate the entire coordinate system, but not under the standard translation, but under the so-called zero translation, which is actually related to this parallel transport thing. So it's basically applying this parallel transport, you can actually translate a coordinate system. So the origin of a system doesn't carry any information, which is a bit counterintuitive, but yeah, that's it. That's what it is.
So I think that's maybe relevant to what I want to ask. What X and Y here are fixed in terms of what?
I think in terms of their distance.
In terms of distance, yeah, I would say they're the same distance, but depending on when you are on the sphere, that's why when you are close to the center, they seem to be connected by a straight line. But as you're moving in the edges, that line bends. So is that right?
Yeah.
That's what I am.
Yeah. It's the distance, if I recall well. Yeah.
And that's why it looks like that the axis is also bending more. It's not behaving very linearly.
Yep. Yes. Should we move on? I have a lot of slides. I'm not
sure.
Yes,
please move on.
I'll be able to cover everything, but I'll try to cover as much as we can. But feel free to send me any also questions afterwards. I'm really happy to answer. So yeah. So now we have the concept of Ricci curvature, which is the last type of curvature. And intuitively what it is, so it's measured at a point X and with respect to a vector V in the tangent space of X. So if you want, it's a vector V that's origined at X. And it's just basically measuring the average sectional curvature over all the directions W. And just to give a bit of intuition of what's going on here. So if you look on the left picture, this is taken from this paper. Sorry. So we have a vector Wx, and the endpoint of this vector is corresponding to a point x prime on the manifold. So if we just do a parallel transportation, so we move Wx, we translate it as I showed you in the previous animation to y, then x prime is going to be translated to y prime. Okay. So now we just have to measure how is the distance from x to y compared to the distance from x prime to y prime in this manifold. So if we are in the Euclidean space, it's going to be exactly the same. So xy is equal to x prime y prime. But if we are in the spherical space, x prime y prime is going to be smaller than xy. If we are in a space of negative curvature like hyperbolic space, it's going to be larger. And this gives another intuition on this concept of curvature. People have taken this Ricci curvature concept to discrete structures like graphs. And for graphs, you can actually do it for every node. And instead of a vector v, you just take adjacent edges v. And they have used this to measure, let's say, the curvature of edges in the internet graph, internet topology. And you can actually see here on the right side, on the left side, sorry, Ricci curvature of every edge on this graph. So green means Euclidean, and then blue is more like spherical spaces, and red is hyperbolic or negative spaces. So you can see that the core backbone edges or links in this internet topology graph, they correspond to negative Ricci curvature, which is again a motivation of why using hyperbolic spaces might be a good idea for some types of data. I have to say that this internet topology graph is like a type of scale-free network that I was talking about before. So a few nodes are kind of central, and they carry central information, and many nodes are just let's say leaf nodes. Okay, and here is just a summary of curvature and how triangles look like, some of triangles. And maybe interesting is like how the, let's say, circle length and disk area behave. So yeah, you can see that for hyperbolic spaces, we have this sin h of curvature, of square root of curvature times radius, which is like an exponential growth in the radius. Okay, so if we want to use hyperbolic spaces in machine learning, then we have to use Riemannian optimization. And what is Riemannian optimization? It's essentially a generalization of Euclidean tools. Let's say a generalization of stochastic gradient descent, which is called the Riemannian stochastic gradient descent, RSGD. So in SGD, you know, we update a point u by saying it's the new update is u minus learning rate times the gradient. Okay, in Riemannian manifolds, we don't have a concept of adding two vectors, but we do have a concept of similar concept, which is called the exponential map. So what people do is that they just take the exponential map at the current iterate u, and then they apply minus the learning rate and times what is the so-called Riemannian gradient, which for spaces of constant curvature is just a rescaled Euclidean gradient. So it behaves very well, and it's computationally very efficient. So you can actually see here on the right side how the Riemannian gradient is computed from a Euclidean gradient of a point u, and R here is just the norm of the vector u. So it's just a simple rescaling using the norm of u.
Can I ask something? Could you just absorb this correction to the learning rate? Would it make any difference, especially if you're doing adaptive learning rate?
Well, not really, because it depends on the point u. So for different values of your embedding u is going to be different.
Oh, I see. So if you were using a constant learning rate, it wouldn't adjust from point to point.
It doesn't depend on the gradient. So it's not like in Adam where you absorb the history of the gradient in the learning rate. Here it depends on the current iterate, the current point u. So I'm not really sure you can do that.
No, you're absolutely right. You know, because you.
Yeah. I'm not. Yeah. I'm not sure you can do it, but I'm also not 100% sure it's impossible. But anyway, you also have this exponential map on top of it, so it gets a bit complicated. And anyways, so this provides the fundamental motivation for why we cannot just plug and play the hyperbolic distance into standard machine learning pipelines. We also have to use Riemannian optimization, which is giving a fundamental difference. Okay, so I was mentioning this hyperbolic and Poincaré embeddings paper before, which is the first one that has tried to do hyperbolic embeddings. So what they want to do is to measure similarity in hyperbolic space. So they take the word net hierarchical structure, let's say here just the mammal subtree, and they embed it in the space such that the distance, the hyperbolic distance between two concepts U and V is small if they are connected in the transitive closure of this graph, of this tree, and it's far if they are not, right? So this log likelihood loss function is capturing exactly that. And it turns out that they obtain amazing results, like with only 5 dimensions, they can beat by far Euclidean or translational models for, like, let's say 200 dimensions. And a question is, what is going on? And here is like a 2D visualization. So I basically trained here their model in 2D, and you can see how it evolves during, so here the black lines are the edges of the tree. And you have Euclidean on the left side, hyperbolic on the right side. And you can actually see that the Euclidean embeddings, they are a bit chaotically organized in the space, in the sense that the embeddings of some of the leaf nodes are close to the root or close to the other branches of the tree. So they really don't reflect so well what we were hoping to reflect, like close if they are close in the tree, in the tree graph, or far if they are farther. But in the hyperbolic space, on the other side, it looks much better. So they seem to be organized and disentangled. The branches of the tree seem to be well disentangled. Of course, it's not perfect, but again, this is just if you increase dimension, if you set it to 5 instead of 2, then you actually get almost perfect disentanglement. So maybe this gives an intuition of why these spaces are nice. Okay, so what we did on top of this paper, in our ICML paper, was to generalize their concept of, so in their paper, they just use a symmetric distance between two nodes, and we want to capture hierarchical structure in the sense that we also want to capture directionality in the graph, in the edges. So we want to capture the entailment concepts. So V, the subconcept of U, which corresponds to direct edges in a directed acyclic graph. So we don't want to embed just undirected graph, but a directed acyclic graph. And of course, to use hyperbolic geometry. So the previous paper, they had an experiment where they did something like that for WordNet, but they used a heuristical approach, which was not trained, was just use the test time. I'm not going to cover about that because we don't have enough time. There is also another baseline, which is called order embeddings, where their goal is to just put hierarchical structures in the Euclidean space, in the so-called concept of entailment cones. So let's say we have the entity person. So we want that the entire quadrant, the green quadrant, if you look on the right side of person, corresponds to embeddings that are subconcepts of person. So let's say woman is a subconcept of person. So we want it to be in the quadrant, in this upper right quadrant of person. On the other side, skis, let's say, is not a subconcept of person, so we don't want skis to be embedded in this quadrant of person. So that's their intuition. And if we embed, let's say, a tree, like we did here for a butterfly data set. So here is a data set showed as basically a set of trees, and here is how it looks like in the embedding space, or using order embeddings. So what we did in our paper was to generalize this concept of entailment cones to convex entailment cones, and we did it for any Riemannian manifold. And these cones, they induce a partial order in the embedding space. The order being that if U is a subconcept of V, then the embedding of U should be placed inside the entailment cone of V, entailment cone of V. So it's exactly like woman is a subconcept of man, then woman has to be in the cone of man, person. So woman is a subconcept of person, then it has to be embedded in the entailment cone of person. So in order to generalize Riemannian convex cones, we just use the concept of tangent space and exponential map. So we know how to do entailment cone, convex cones in Euclidean space. So we had a simple idea of doing it in the tangent space of a point X. And then we just project the entire cone on the manifold using the exponential map. And that defines what is called Riemannian convex cone. So we require like 4 properties that are needed, and then I'm not going to cover. It's basically some simple properties. Maybe just the last one that's needed for this being defining a partial order in the embedding space, which is called transitivity. So what we want essentially is if X prime is a subconcept of X, then we want that every subconcept of X prime is still a subconcept of X. So just to give you an example, let's say dog is a subconcept of animal. Then we want, let's say Dalmatian, which is a subtype of dog, to also be a subconcept of animal, of course. So in the embedding space, this translates into the fact that if X prime is in the convex cone, entailment convex cone of X, then the entire convex cone of X prime should be fully included in the entire convex cone of X. So in the picture here, X, let's say, is one of the small triangles that have a light green cone attached to it. And then X prime is let's say a subconcept, which is a small triangle that has a dark blue cone attached to it. So you can see that the entire dark blue cone is completely included in the light green cone of X. So we desire this to happen, because otherwise the embedding space is not gonna define a partial order relation, which is needed for capturing this hypernymy or entailment concepts. So in our paper, we actually prove that having these 4 properties is enough to define a closed form expression of the cone at every point X. And the expression is given by this formula here. It's actually this formula. It looks a bit ugly, but computationally it's very efficient to implement, and yeah, gradients are flowing properly, so everything is behaving very well. So again, I'm not gonna, because of time limits, I'm not gonna get into details of this, but you can read the paper, and there are some proofs there that shows how we got to these closed form expressions. The good part is about it is that now we can actually put all of this into a loss function. And yeah, so I'm gonna cover it in a second. So these 4 properties, as I said, they induce closed form expressions of entailment cones for different points. And here you can see for different triangles, so different points which correspond to the green triangles in the hyperbolic space in the Poincare ball, we show the corresponding entailment cones. And a similar derivation was done also for Euclidean. So you can do a very similar approach for Euclidean angular cones. So the advantage here over order embeddings is that the cones, they now extend in all the directions of the space and not just in a single direction. So as you remember, I was showing that these quadrants in order embeddings, they are always expanding in the upper right direction, right? But in this case, the cone is expanding in all the directions. So this actually shows why this exploits the space in a better manner.
Yeah, so you make better use of the space. That's amazing.
Yes,
While you know with you.
Yes.
So that was my
because-
question. The whole concept of the cons is to better capture the hierarchy, right? Inherent in the data. Not only the hierarchy, but also the distance, I guess.
Yeah, I mean, in this paper, you only looked at capturing the hierarchical structure. And in the paper of where we used, where we trained word embeddings, which is a different paper, the one that I mentioned before, then there we also try to capture similarity and word analogy. But here we just focus on the same setting as order embeddings, which is like capturing just the hierarchical structure when the hierarchical structure is known. Yeah, so we just use a similar max margin loss function like order embeddings did, except we used our formula for entailment counts, and we had to use Riemannian optimization. But everything else stays the same like in order embeddings in terms of like the loss function is very similar. So we also did some qualitative experiments. Oh, I'm really sorry. We also did some qualitative experiments, and I'm showing here like the WordNet mammal subtree on the right side, and on the left side we have a uniform tree of depth 7 and branching factor 3, and this is how the embeddings look like when we compare Poincaré embeddings, and which is on the left side, and on the right side is our hyperbolic cones. So you can see that the Poincaré embeddings are somewhat collapsed, whereas our hyperbolic cones, they are at least visually nicer or somewhat nicer. We also went and embedding, so here I actually compare order embeddings of again, like synthetic trees of a fixed branching factor and fixed number of levels in the tree. And this is order embeddings. And here is using our version of the Euclidean cones. So you can see that now they expand in all the directions of the space, which is kind of nice. And then we also did quantitative experiments, link prediction in the WordNet. Here we followed previous work, and we obtained some nice improvements over the baselines that we considered. And I have to say that training is a bit tricky. So we find out that it's very important to initialize with pre-trained Poincaré embeddings, which don't take the direction of the edges into consideration, but they still provide a very good initialization. If we don't do that, then our model has very hard times escaping like bad local minima. And we have code that you can check out. Yeah, so here I'm also showing again Euclidean cones for the data set that I was mentioning before, which is a butterfly species data set. Yeah. And some performance here that I'm gonna skip now. And yeah, a few more results. So you can check the slides if you're interested in details. Okay, so last thing that I want to cover in the few minutes that I have left is the paper at the spotlight paper at NeurIPS 2018, which is talking about how we can use these hyperbolic embeddings in neural networks, or deep learning, or which with the goal of having this used in downstream tasks. Does it make sense to just feed these embeddings as inputs to traditional neural networks or deep learning architectures like ResNet, let's say? Yeah, practically we can do this, and there are people who attempted to do this, but without getting very good results. And in theory, at least, hyperbolic geometry is going to be ignored if we don't use operations that make sense. For example, it doesn't make sense to add two vectors in the hyperbolic space, because let's say simply the addition, it makes no sense, and the addition of two vectors might even get out of the domain definition of the hyperbolic space, which the model that I explained before was a Poincaré ball, so a ball of fixed radius. But it doesn't follow the geodesic. Yes, and
so just to understand what you're doing here is, can I ask a question? You're just taking a fully connected, neural networks with traditional ReLUs, and in the objective, you're saying that the distances have to be hyperbolic, or what did you mean by fitting into ignoring the?
So already,
what exactly are you trying to?
So already setting a linear layer on top of a hyperbolic embedding makes no sense, because a linear layer is just a matrix vector multiplication, right? And that operation is not defined in the hyperbolic space. In fact, if the matrix is a vector, then it corresponds to a dot product, right? So that also doesn't make sense. And if
so
you
I see
add
what you're saying. You're saying, so basically, you're saying take the hyperbolic embeddings and feed them into as extra, into traditional neural networks.
Yes, I'm saying that this doesn't make sense in theory, and it's just ignoring the hyperbolic geometry. It's just acting like the hyperbolic embedding would be an Euclidean embedding with the Euclidean geometry, which is not true. So I'm going to cover it in the next slides, and if it's still unclear, we can talk after I show these slides, maybe. Okay. Can you hear me?
Makes perfect.
Okay. So as I said, we have to use Riemannian optimization, and we have to enforce hyperbolicity of, let's say, hidden states if we deal with like feed-forward networks or recurrent neural networks. So standard operations like vector addition, matrix vector multiplication have no meaning in the hyperbolic space. Vector addition should follow hyperbolic geodesics or straight lines, like I'm gonna discuss immediately. So our idea is to use a generalization of vector spaces, which is called zero vector spaces. So this is a framework that generalizes, that is gonna be used to generalize neural networks to hyperbolic spaces. So that's the main contribution of this work. So these zero vector spaces, they are used in relativity theory because particle speeds are also hyperbolic vectors. And why is this? If you add two speeds, then they should never exceed the speed of light. So the speed of light, if you want, is like the radius of this Poincaré ball. So all the speeds, they have to lie inside the hyperbolic space of this specific radius. And the zero vector spaces, they provide an analog for Euclidean vector spaces. So let's briefly talk about them. So how do the standard operations change? The vector addition is now looking differently. So here the vector addition depends on C. So C is the curvature of the space. So if you put C equals 0, you can actually, which corresponds to Euclidean space, you can actually see that you recover the true x plus y that you knew for Euclidean geometry. If you put C negative, then you get what is the vector addition in the hyperbolic space. If you put C positive, you get vector addition on the spherical space. We also have the concept of scalar vector multiplication, which is again shown here. So the formula is a bit more complicated, but it's still like before. If C goes to 0, so if we kind of converge to the Euclidean space, then this is gonna become exactly under the limit. It's gonna become R times X as you know it, the standard scalar vector multiplication in Euclidean space. So these operations, they satisfy a few interesting properties, like properties that you would hope for. Let's say associativity, scalar distributivity. Commutativity is not satisfied, but it's interesting that is something that is called zero commutativity, which has some funny properties, and left cancellation law and others. Okay, so we use these two concepts, and on top of them we build. Oh, so sorry. So I also have to say that we have a closed form expression of the distance, let's say in a hyperbolic space. So the distance that I showed you before was having some r cos h and some more complicated formula, but it's actually the same as the formula that's shown here. And here you can actually see that it looks a bit like the Euclidean distance as you know it, in the sense that you don't have the norm of minus x plus y, but you have the norm of minus x O plus y. So O plus is like zero addition. So, and on top of it, you have to put some tan h minus 1. So again, if C goes to 0, so the space deforms to Euclidean space, then you fully recover the Euclidean distance. And geodesics, they look actually very, very similar to the Euclidean geodesics, except except that we use this plus and this times instead of the standard plus and times. Yeah. So again, as I said, all formulas recover the Euclidean variance when the curvature, which is minus c, goes to 0. So what we did in this work is that we derived closed form expressions for parallel transport and for exponential and logarithm maps, which are needed for, let's say, Riemannian optimization. So exponential map now looks in closed form like it's shown here. And then we went over and we designed hyperbolic feed-forward neural networks. And our idea is to adapt nonlinearities by just using the so-called concept of logarithm and exponential map at a point 0 or the origin. So what we did was to take a point x, which is in the hyperbolic space. We lift it up in the tangent space at 0. Here, the tangent space at 0 is the Euclidean space. We apply the nonlinearity, and then we put it back on the manifold using the exponential map. And we did the same for matrix vector multiplication. So why we decided to do it like that? It's because the scalar vector multiplication that I showed you before, it's doing exactly the same trick of going in the tangent space of 0, applying the scalar multiplication there, and then going back. So yeah, so the matrix vector multiplication satisfies these desirable properties that I'm not gonna cover now. And then we also have to generalize bias translation. And here we use the O plus operation that I showed you before. And it turns out that you can actually write it in a different way, which is you lift up the point B in the tangent space at 0. Here you do a parallel transport from 0 to x. And then from x, you put it back on the manifold using the exponential map. So all of these operations now are enough to define feed-forward neural networks. And of course, we can do also vector concatenation. It's just a simple generalization. Again, all models recover their Euclidean neural networks as you know them when the curvature goes to 0. So when the space is deformed to Euclidean space. What we have to do next is to generalize softmax layer or what is so-called multi-class logistic regression. And here we followed previous work and we took a different view on the softmax layer, which is, let's say we have data X and it can have one of the K classes. So in the softmax layer, what we do is that we learn a vector. So in the softmax layer, we apply a linear layer and then we apply the standard softmax function. This is actually equivalent to learning an AK vector for each of the K classes, taking a dot product with X. This gives us a real value, adding a bias, BK, and then this is like the final value of the logit for this specific class. And by gathering all the K logits, we just apply a softmax function on top of it. So this is actually equivalent, as I said, to the standard softmax layer as you know it. So you can actually reformulate this as a signed distance to a hyperplane in the Euclidean space. So hyperplane is defined at a point P and an orthogonal direction A. So it has this equation here, like the dot product between X minus P and the orthogonal direction A has to be 0. And if you just rewrite the first equation on this slide, you'll get a different formulation, which is essentially saying that the softmax probability is just a sign of value, which tells us on which side of the hyperplane the point X is. So it's plus or minus 1. And then we have the norm of the orthogonal direction or of the normal direction to the hyperplane, which you can set it to 1. And then you have this interesting quantity, which is the distance from the X to the hyperplane. So what this is saying is that if we are far away from, if X is far away from the hyperplane, that we are more sure about the class of X. But if X is very close to the hyperplane, to the margin, let's say the margin of our classification, procedure of our classification model, then we tend to have a smaller logit value, so we are not so sure about the class of this point X. So that's exactly what the softmax layer is saying. And now using this last equation, we actually needed this in order to generalize it to the hyperbolic space or to a non-Euclidean space. And the first challenge was to define what is a hyperbolic hyperplane. And we did it in a very analog manner to the Euclidean space, except we now use the new plus, the new zero addition. You can actually read the details in our paper of why this makes sense and why this is a good generalization. And we also obtained a closed form expression of the distance, but now is like the hyperbolic distance from X to the hyperplane. So this is like the smallest distance from X to any point lying on the hyperplane. And that's the final formula for our hyperbolic softmax. So it looks a bit like the one before, except we have a few more concepts like inverse of C in H and a denominator. But what's very nice about it is that actually when the curvature goes to 0, then again we recover the standard softmax layer. And here I'm showing an animation of a 3D animation of how a hyperplane is looking like in the case of 3D hyperbolic space. So the green plate, if you want, subplate, is like the visualization of the hyperplane. And the red point is the point P where the hyperplane is, let's say, defined, and the line is just the orthogonal, the normal direction to the hyperplane. So as I said, we recover the Euclidean variance when the curvature goes to 0. And here I'm showing an animation of how the distance to the hyperplane looks like. So it's basically a heat map of the square root distance to the hyperplane. And what I was showing before was only for hyperbolic spaces, but here we also have it for spherical spaces. So yeah, so when K is positive, then we have a spherical space. So here's the stereographic projection of the sphere. When K is 0, we have the Euclidean space. And when K is negative, we have what I showed you before, the hyperbolic space. So we have more cool animations on our blog. So Andreas, a former student of mine, has made these nice plots. So you can feel free to check them. Yes. Okay. So the last contribution of this paper was to design hyperbolic recurrent neural networks, and we focused on RNNs and gated recurrent units. And since I'm running a bit out of time, I'm not going to discuss too much, but it's essentially, we just use these new operations instead of the Euclidean operations, and we showed why this makes sense. And we also recovered the Euclidean RNN and GRU when the curvature goes to 0. So we did some experiments. One is to do classification. If we are looking at let's say, subtrees of the Warner tree, we embed them with Poincaré embeddings, like the paper that I talked about before. And then we want to use, let's say, the softmax layer that we designed, the hyperbolic softmax layer, to classify them as being part of the subtree or not. So here we have different dimensions, 2, 3, 5, 10. And then we have the hyperbolic softmax layer, we have the Euclidean softmax layer, and we have log 0. So log 0 is essentially a baseline where we take the embeddings in the hyperbolic space, we lift them up with a logarithmic map to the tangent space of 0, which is Euclidean space. And we just do a standard classification like softmax in that space. So you can see that our model is most of the time beating these two baselines.
Yeah, very impressive differences. Although I see in the first, as you increase the dimension, on the second, they all tend to come close, but in the last two, the differences are pretty significant.
Yeah, yeah. I have to say that this hyperbolic embedding so far, most of the people have seen impressive results in low dimensions, but not so much in high dimensions, with the exception of the tables that I showed you in the beginning for WordNet. And I mean, this is still part of ongoing research, like how to make these models also work very well in high dimensions. It might be also, I mean, we have also seen, many people have seen that optimization is actually very difficult in these spaces. It's much more difficult than compared to Euclidean spaces. So here you can actually see a bit of intuition of why we got these nice results. So here in 2D, the green hyperplane, we have the two green hyperplanes. Left side is hyperbolic, right side is Euclidean softmax, so Euclidean hyperplane, so it's a straight line. And you can actually see that since let's say the hyperbolic hyperplane is banded, then it's able to leave out most of the yellow points, which are just false negatives. Sorry, false positives. So we also did experiments on textual entailment, like SNLI and SNLI dataset and some synthetic dataset. So I'm not sure I have enough time to talk about them, but yeah, you can read them in our paper. So I just want to conclude that yeah, I hope you enjoyed this talk, and of course we looked at spaces of constant curvature. There are still many challenges, like how to do optimization, and then how to adapt hyperbolic, how to adapt deep learning tools, and how to make them be state of the art in different tasks. Like, let's say for images, there is no paper that really obtains state of the art results on images so far. So that's very interesting. We are also interested to look into other tractable types of geometry. So the good part about spaces of constant curvature is that you have all these quantities like distance, exponential map, geodesics. They're all in closed form. So you can actually put them in a machine learning model, and you don't suffer in terms of like computational inefficiency. So they're actually very nice, and it's very important to have them in closed form also because of backpropagation. So you want gradients to flow properly. So yeah, so that's very nice. So we started looking also at matrix manifolds, and we're gonna have a submission at ICML this year. And how to combine spaces of different constant curvatures. There is a paper, product of spaces, that I have on the next slide, and also how to do generative models. So
that would be cool to see some GANs on. Has
yes.
anybody tried that? Not yet.
Not that I'm really aware of.
Is there a difference when you use convolutional networks, or it should be the same? Or are there, you presented a fully connected layer, but CNN should be similar since they are equivalent?
I know people have tried that for images, but it's a bit unclear in images, like how you would embed every pixel as a different point in the hyperbolic space, or I mean, it's a bit unclear how to do it. People have, I know at least one paper that has tried to generalize convolutions, but they couldn't beat state of the art. So yeah, that's what I know. So yeah, so feel free to check our blog posts that are listed here, and yeah, we hope in this blog post to provide a more introduction and more easy to read resources for people that don't have time to read the papers into details or other references. But I also put here a bunch of references that you might find interesting. Of course, they're far from being complete. So yeah.
Thank you very much, Octavian. It was really amazing. I mean, I'm a big fan of this work, and I wanted to share that with my colleagues. I don't think we have time for. I don't know if anybody has questions. I probably have to drop because I'm already late for other meetings. I will definitely download and share with you. We'll also upload it on YouTube, so you can share it with other people as well.